Hi, we're Group 9, and we will be showcasing JASE, the restocking robot. Holsworth has contracted an autonomous grocery store restocking robot at the TRL-3 stage to Group 9. This robot would address the needs for automated restocking in stores by reducing manual human labor and ensuring safe/effective handling of items. Constraints. For a successful prototype, the robot must adhere to the following constraints. It operates safely with the human, store, and grocery items. It has LED indicators to communicate phases. It fits within the starting spatial constraints of 20x20x20, and a TRL-3 prototype made under the $200 budget. For the demonstration, the robot starts at the initial position here, then autonomously navigates to the picking station here, collects the items, and then delivers it to the shelving area, as specified in the order file, all while avoiding obstacles in its paths. It repeats for 3 runs. The robot JASE achieved most objectives. However, although obstacle avoidance was designed, it could not be implemented for integration due to time constraints. Sensor and calibration issues also prevented the second and third shelf runs, although this can easily be addressed for future iterations with improved calibration and sensors.
My name is Alex and I was responsible for the navigation subsystem. Initial development of navigation began in a simulated environment. After exploring various control approaches, a finite state machine was selected for its simplicity, an important consideration given the restricted timeframe, deterministic potential, and repeatability across order sequences. In this setup, the robot navigated using unobtainable shelf bearings and hard-coded time delays, which proved unreliable and lacked adaptability. Serving as a foundation, the integrated solution expanded upon this by introducing a time-of-flight sensor in place of the time-based controls, as its measurements covered limitations in the vision system, such as when positional markers were partially occluded. This allowed it to behave reflexively in the conditions of the environment, where time-based controls initially executed fixed, open-loop movements. Navigation was informed by a CSV formatted order file, where each record was specified in item's picking station, target shelf, bay, and height. These parameters were translated into stopping distances relative to environmental markers. In the hardware loop of the Raspberry Pi 5, the vision system continuously supplied the navigation algorithm with arrays of visual data. In mobile states, proximity and bearings to stimulus were translated into proportionally controlled PWM signals to independently drive each motor, achieving both linear and rotational movement. Object recognition worked in tandem with item collection by correlating detected object characteristics to actuator strength, ensuring precise handling and preventing motor overexertion. Navigation also coordinated the elevation of the collection arm and updating of the RGB LED to display operational statuses. Green for collecting, yellow for transporting, and red for depositing. The modular nature of state machines allowed for iterative testing at different stages of development and for different order configurations. Proof of concept for obstacle avoidance was developed in the simulated environment, where obstacle proximity triggered a predefined sequence of movements around hazards. This was unfortunately not translated into the final product given the limited timeframe.
I'm Evan and I've been assigned to the vision subsystem. The vision subsystem is responsible for detecting the warehouse environment in real time and supplying the navigation subsystem with essential spatial information like bearings and distances. The PyCam Module 3 was selected to capture the environment as its FOV, suitable resolution, and autofocus was ideal for the proof of concept. Additionally, OpenCV library was used to perform color filtering, contouring, flood filling, and other helpful operations. To estimate the distance to the warehouse environment, the pinhole camera model was used. To determine the distances, it applies trigonometry, relating the object's true height and distance from the camera, and the object's projected height on the sensor and the camera's focal length. Additionally, a time-of-flight sensor was implemented to obtain distances to subjects that weren't entirely visible to the camera. To estimate the bearing to the warehouse environment, the subject's horizontal pixel position was measured, and the angular displacement was calculated by multiplying the pixel offset from the image center by the ratio of degrees per pixel. Besides bearing and distances, additional logic was developed to determine the type and number of markers.
Hello, my name is Joseph and I was in charge of the mobility subsystem. The mobility subsystem is responsible for the movement of the robot and connecting the other subsystems together. After several design prototypes, a semi-enclosed tank track system was chosen. This design allowed for most of the sensitive parts, like the Pi and battery, to be contained, while still being easily accessible. This chassis was also almost entirely laser cut, meaning that it was incredibly modular and could be quickly iterated upon. It needed to move forwards and backwards, accurately turn on the spot, and power the other subsystems. To allow for the item collection subsystem to work with mobility, I had to communicate heavily with Zenith on what design choices were required and what things I had to change. This included things like specific measurements for the mount and cutouts for the item collection arms. One big issue with the mobility subsystem is that even with the new motors we ordered, the right motor wasn't strong enough and didn't consistently drive at a set speed, something that significantly impacted the final demonstration.
Hi, I'm Zenith. I worked on the animal collection subsystem, giving JASE the ability to interact with the real world. The mechanical design consists of parallel linkages for elevation and rack and pinion for gripping. The parallel linkage raises and lowers end effector upright with accurate vertical displacement from the ground to the upper shelf. Most of the subsystem was made from 3D printed PLA Plus parts with aluminium rods, used as well for light, weight, and strong structure. It also ensures the robot remains in spatial constraints at startup. Nylon inset nuts were used to prevent loosening of bolts over time. The rack and pinion mechanism allows for simple linear opening and closing of the grippers, providing a secure grip. Various difficult objects were successfully grabbed thanks to the rubber bands used on the claws to improve friction and surface contact area. Both servos are connected to a custom servo PCB hub, ensuring clean cable management and ease of maintenance or repair.